My name is Vladimir Bulovic, and I'm a professor of electrical engineering who is extremely lucky to have had the chance to have an amazing graduate student, Richard Swartwout. Rich has joined our lab first time as a summer student back in the summer of 2014, where with vast experience in chemical engineering and material science from RPI, he decided to spend the summer in our lab. What I remember from those very first meetings that he attended in my research group is here's a student, an undergraduate, who has ideas and directions that none of my present students had. One who can actually think about materials with an angle and agility that none of us in our laboratory had exposure to. So when Richard asked me for a recommendation letter, it was very easy to write. When he got into MIT, it was a joy to try to recruit him to join my lab. And I was lucky enough to actually have him start with our laboratory back in September 2015. His journey has achieved a lot. He started at the time when perovskite solar cells, which is the topic he'll cover today, have been in their very nascent form. And yes, there was an opportunity to scale them. Yes, there was an opportunity to stabilize them, but how to do it was very, very much missing. Rich, in his work and by working with colleagues around him, came up with a number of ways to solve problems that seemed unsurmountable back when we started in 2015. And yes, there are still a few more issues to be resolved, but Rich's pantheon of solutions is bound to be used as this technology keeps on progressing. That being said, rather than tell you the rest of the story of all of his amazing work, because I wouldn't do it half the justice that Rich can through his words, I'm going to stop and ask Richard to take over. I'll just conclude by saying it's just truly been a joy to see how Rich has evolved over these years. And I do very much expect you will very much enjoy the presentation he's about to give you. Please take over.
Thank you, Vladimir, for the very kind introduction. Happy Friday, first of all. So I hope this is the last meeting for all of you for the day. Like Vladimir mentioned, today I'm going to be presenting my PhD work for the last roughly 4 years or so on scalable perovskite thin film photovoltaics. For everyone in the crowd who's not an academic, photovoltaic is just a very extended term for solar cell. And if you haven't lived under a rock at all for the last 6 years that I've been in grad school, you'll probably realize that silicon-based solar cells are pretty much a scaled technology. They have an R&D backing of about 70 years. The United States imports from China about 3 gigawatts every month throughout 2020 and 2021. And probably all of you, at least within your own neighborhoods, or maybe even you own them yourselves, have seen residential installations or utility scale installations. So this really begs the question, and what I really want to start off with is, why are new solar technologies still necessary with all that backing, with a technology that appears scaled? And the way to answer this is really by breaking it down into 3 questions. The first is, why should we move to more lightweight and more flexible based solar technologies? Why is thin film potentially better? And why should we be pursuing thin film technologies like perovskites, which I'll be talking about? And why should we be thinking about alternative manufacturing methods like printing and coating, which will also be discussed here today? To start things off, I think it's really important to discuss the actual land area needs for solar. So if we take the US continental 48, the entire energy demand, if we met it today with solar, would require about 2 to 3% of the entire land area of the country. This is roughly the size of Illinois, just to put that in perspective. But we, by 2050, are going to expect a lot more electrification, especially in cars and removal of fossil fuels. And so by 2050, this is actually expected to grow to about 8 to 10% coverage of the United States just to meet total energy demand. So you can think of this like an upper limit. We have a long way to go. So at the end of 2020, we had about 100 gigawatts installed, and this represents about 3% of the total energy demand need of the United States. On the surface, this seems very achievable. 2 to 3% of land area is really not that much, especially when you look at census data on kind of how the land area is broken down within the United States. About a third of the United States is shrubland, about 20% is grassland and pasture, about a third of it is forest, and only about 3% of it is directly urban. So things that are paved over, places like Boston. So from just this, it appears on the surface that we have like kind of an abundance of land, and this is very easy to achieve. However, you would be a little bit wrong to assume that. And just to give a very simple example, by 2050, there's going to be about 500 million people living within the continental United States. And to offset the CO2 generated from those people, we need about 50 to 60% of the United States to be covered in forest. And again, this is a very simple example, but I think it's pretty clear that land is actually not a surplus, despite the fact that we don't use a lot of it for urban productive purposes. And so hitting these 2 to 10% coverage is actually going to be relatively difficult. You could say, well, let's use other renewable energy technologies like wind, but it actually turns out that wind needs more land area, so about 8% to meet energy today, about 33% by 2050, and obviously that's unrealistic. It's a little bit of an aside, but I think this is probably one of the biggest cases for offshore wind. It's one of the only energy assets that can be shoved off land. And so, this is definitely something that the United States should be pursuing down the road. Another way to really think about this is to ask the question, well, where are the people and where are we using electricity? And the way to think about that is shown here. The gray is urban areas, again, constitutes about 3% of the land area of the United States. Mega regions, which are economic and travel regions and hubs within the United States, are shown in orange. This is taken again from census data. And it only constitutes about 23% of the land area. So, there is a lot of, again, land outside, but we're only basically using economically about 23%. Solar installations today, it's probably pretty clear from the last map in this map that follows these sort of mega regions. And so with a little bit of Photoshop magic, I can overlay both of those maps. And you can see a very clear trend that solar is really only installed in and around where people are and where electricity is. But we're not installing it fully urban, and we're also not installing it fully rural. And so that's kind of a key conclusion from all of this talk, which is that solar is primarily a suburban generation technology. It's really only being installed kind of on the edge of where the main economic grid is. And there's a pretty clear reason for this. It's actually very simple. Of all the places that we could be installing solar today, obviously the most common is using undeveloped greenfield land. We could be repurposing brownfield, grayfield, and you can also think of other different installation aspects like integrating with buildings and using things like roofing, or building retrofit, which is the common mode for residential systems. However, the reason why we're seeing a lot more, especially utility scale solar at the greenfield level, is because it's just fundamentally more expensive to develop on reused land or to integrate into buildings. And so again, this entire conclusion is that, we don't have a surplus of land. We need to start penetrating these other sorts of installation metrics. And we need to do it either by moving fully rural and start integrating more like off economic grid, or going fully urban. And so these markets actually exist. People have been touting this for a while. So if an example of an urban PV system is something like this. It's a steel superstructure with, silicon-based PVs today. I think everyone kind of wants this a little bit, which is, you know, solar cells that sit above a parking lot. It shades your car, but also generates electricity. And we actually have enough paved road in the United States to cover all electricity need for a purpose like this. If we go fully rural, the easiest way to do this is through agriculture. And so there's a term called agrovoltaics. Not every plant needs 8 hours of direct sunlight a day. A lot of fruits only need partial shading. And so you can achieve that and use the wasted sunlight again to generate electricity. This is a installation, again, a steel superstructure with a glass PV module mounted on top to provide a little bit of shading and protection for the plants below. Now, despite where I picked on this map, the northeast here, where there's not a lot of utility scale solar, this is actually the California Department of Water. So it's definitely an installation. I have to run back to the on-time supplies. The Pacific Northwest installation that I marked off here, it's actually not even in the United States. This is in a winery in France, which has been using, again, it's not their full winery, but a very small installation to help protect the grapes due to climate change. And so these are very not common installation methods and are very expensive. Again, it's just throwing I-beams at the problem. It's unrealistic to assume that we're going to be able to utilize more productive reused aspects of land just by building steel structures above them. If all you're interested in is shading, the way that we do this economically today is by flexible installation methods. So this is an image from Madrid, Spain. These tilings above this shopping street, they're called shading sails. It's just a steel cable hanging with a little flexible net to provide a shade to the pedestrians below. If we do this with agriculture, obviously the most common method is just netting. So this is in India for fruit plants that, again, don't require 8 hours of shade. Yeah. If we were to sort of, again, harvest the unused light in these sorts of installation methods, both are flexible-based installations. So it makes much more sense to have a flexible-based solar cell to help, again, reuse this light that's generally being wasted into more productive electrical means. If you're familiar with the industry, though, you're probably saying, but Rich, flexible silicon cells exist. SunPower markets them all the time. They're, you know, it's an established product. So shown here is the flexible PET SunPower cells that have been on the market for a while, and they just offshot Maxeon, which is their cell manufacturer, which is coming out with a steel-based installation method called Maxeon Air. The thing is that there's fundamental limitations to using silicon. So if we take one of these SunPower cells, and this is just a normal photo image, you can't see much with this using this sort of method. So if you look at these cells under a photoluminescence inspection system, you'll see something like this. They're not always perfect, like this one. In the unbent state, it looks like this, but if we bend it, before I show that image, I just want to reintroduce geometry for bending. If you 2-point bend something, you can think about it as defining a circle. The radius of that circle is called the bend radius. So a higher bend radius means a larger circle and therefore a smaller degree of bending. A smaller bend radius therefore means a higher degree of bending, right? So if we take this SunPower cell and we bend it to a radius about 60 millimeters, we start introducing cracking into the cell, which permanently damages specifically this cell, making it non-functional. This is a fundamental limitation to silicon. It's a brittle ceramic material. It is in a large area wafer format, and so it's really hard to get around this. Thin films, on the other hand, we can print them on very flexible plastics. So this is an image that I'll talk more about later, but perovskites in general are, you know, they don't have this fundamental limitation. So if we look at printed cells underneath the same photoluminescence inspection system, an unbent film looks a little bit like this. Yes, I know it's not super perfect, but again, there's still work needed to be done in this field. When we bend it to a bend radius about 5 millimeters, this is roughly the diameter of a Sharpie, you'd be pretty hard pressed to tell that these images are different. They are in fact different, I can guarantee you that, but there's basically no change with the fundamental material. It's only when I deliberately crease the system and crease that underlying plastic substrate where you see any change at all. So that, I mean, it's the little line here, just to point it out. And it's not a crack. As you can see in the previous images, when you bend a cell and a crack propagates through a silicon cell, you get PL quenching, that's that dark spot. Here it's actually a PL brightening. Under a real image, you know, there's no cracking, there's no delamination. It's mostly just a substrate damage. And so most likely this is not completely destructive damage. And therefore thin films are actually just fundamentally better at being in flexible form factors than silicon-based technologies. Perovskites, which was in the title of my talk, are very interesting for this purpose. They're interesting because of their efficiencies, but also the academic drive behind them. From an academic point of view, everyone really likes them for a bunch of reasons. They're generally defect tolerant, so this means that we can do a high degree of alloying. They're always tertiary materials, but we can get up to quaternary and 5 components, 6 components, however many, process additives, what have you. You'd be pretty hard pressed to decrease performance with these things. Because of the alloying, they're color tunable, so we can go all the way through the near IR into the UV. I'm not going to talk about it today, but this brings up the idea of tandems. They have a very high absorption spectrum because of their direct bandgap nature. The films I showed previously were about 400 nanometers thick, and they were optically opaque. So that does really mean that we're not using a lot of materials. This has a lot really means it can be economical. They have a very high index. Again, I'm not going to talk about it today, but it means that we get photon recycling effects, thereby achieving high VOCs. And similar to gallium arsenide-based structures, we can get much, much closer to the theoretical efficiency limits for single junctions. The thing that's most important for the rest of the discussion today is that they are simple salts. They're really easy to produce at low cost in kilogram quantity, and they're soluble. That is the most important part, which really brings up the idea that we can use lower cost roll-to-roll printing methods to print these using relatively low capex processes. So on the left is Kodak, a machine from Kodak. This is an 8-bay Revere printer. It cost about $60 million. On the right is a machine at VTT. It's a flexographic machine. These are both the upper limit of size, but these machines are very tunable. You can get all the way down to, very simple ones that we have in our own house a lot of the times. And so there's a lot of tunability, and depending on that tunability, you can be spending probably about $2 to $50 million, depending on the size and tooling and precision. This in itself doesn't mean all that much towards the economics, but printing can be incredibly fast. And so just taking a very simple example of a slot die, which is one of the simpler printing based methods, you inject ink through a die, coat it onto a moving substrate. This process is defined by two main fundamental limits, the low flow limit and the extended flow limit. If you do some assumptions, I'm not going to go through the math today, but you can use these fundamental limits and calculate a productivity limit. And so if you're operating in the low flow regime, you can get up to about 6 gigawatts per year on a single tool. And with a little bit of structural shifting around with the die, you can get up to about 16 gigawatts per year in the extended regime. What this ultimately means, that combined with the cost of tooling, is that you're looking at about 10 to 20 times decrease in the manufacturing capex. And of course, this relates to the profitability of these materials because capex usually pins how profitable the technology ends up being. These are just fundamental limits. And so we need to start considering how engineering comes into play on our upper manufacturing speeds. A hard limit, which I'm going to be talking about today, is regulation. So solvents are not always the safest things in the world. Same with lead. And so the United States regulates materials in two different ways. From a manufacturing center perspective, we have the Occupational Safety and Health Administration, which usually regulates how much a worker can be exposed to a certain toxic material. From an emissions and end-of-life perspective, we have the United States Environmental Protection Agency, which limits how much stuff you can pump into the environment, how you do it, how you clean it, but it also regulates, damage in the field, how it has to be cleaned up, as well as leaching into the environment under end of life. I don't have too much time to talk about it today, but I do want to briefly mention the end of life because it's important for those on the call who work with perovskites. You'll probably have seen research on a drip test that people have been doing to kind of quantify how acid rain can be detrimental to leaching lead into the field. This is fundamentally the wrong test. The real test is the toxicity characteristic leaching protocol. It's a regulated test. It has meaning with a bunch of regulations on what you can and cannot do with products. How it works is you take a product of interest, you deliberately reduce it in size to simulate extreme degradation. You then extract it with an acid buffer to simulate, getting into things like acid rain, but also acidic ground conditions. Filter off everything that's soluble, and then look at the solubilized lead, which can potentially, harm people through groundwater. If it's above a regulated limit, it's toxic, which has, again, implications for regulation through the EPA. If you do this test with multiple different perovskite encapsulation methods, the bare film unsurprisingly leaches much higher than the EPA regulated limit, which is 5 milligrams per liter. But a very standard physical glass encapsulation, as well as a glass UV epoxy encapsulation, and even this last one, which was touted in a very prominent journal as being a way to contain lead, is a triple glass encapsulation method. All do not pass this T-clip test. In collaboration with Munji Bundy and Nicole Moody, who's actually on the call, we developed a chemical leaching backsheet to overcome this problem. Again, under damage, water ingresses into a cell or module. It destroys the perovskite. These are soluble systems. That lead then leaches out. So this happens, again, irregardless of physical packaging. Our method, we apply this backsheet, and then under water ingress, the perovskite's still destroyed, so you're not going to save your cell in that case anyway. But our backsheet chemically reacts and immobilizes the lead within the product. This is actually extremely effective. So if you take the bare film, again, this is printed on PET. It does not pass EPA regulated T-clip testing. But then the barrier film has about 100 times reduction in leaching, and most significantly actually would pass EPA T-clip hazard testing in this scenario. We think this is very important, so we're obviously pursuing IP protection in case anyone's interested. But yeah. For the rest of my talk, I'm going to be focusing mostly on OSHA-based regulations because it, again, has a lot of implications with manufacturing productivity. The United States OSHA regulates, again, solvents and various materials through permissible exposure limits. This is a part per million basis, usually for things like skin and breathing. The OSHA limits to common solvents seen in the perovskite field are shown here. But there are also recommended limits as well that are updated constantly. So NIOSH is a great example. ACGIH is used in industry quite a lot. And just to mention as well, again, the EPA regulates emissions by defining hazardous air pollutants as well. So DMF, chlorobenzene, acetonitrile are all not that great. And at the surface, this doesn't necessarily seem like a manufacturing limitation. but I'm going to give a pretty clear-cut example. You can think of a manufacturing center a lot like a black box where you have a solvent input. That solvent then goes through a coating process. It evaporates into your center and creates solvent vapor. You have a limited amount of solvent extraction. And if you pump too much solvent in and try to go too high, you'll end up building up solvent vapors high enough to make a toxic environment no longer suitable under OSHA regulation. The only way to fix this is to stop manufacturing. Again, I'm not going to go through the math today, but this concept was then extended into a generalized manufacturing limit where we define gross air exchange rates. This is not, if you work in clean rooms, you'll know that sometimes air exchange rates can be quite high. This is a solvent extraction air exchange rate, so fresh air from directly outside in rather than internal through HEPA filtering, versus an exposure limit as defined. And just moving from something relatively toxic like DMF to something a little bit more benign like THF, which is used pretty commonly in epoxy-based coating systems, you get about a 22 times higher productivity ceiling than the traditional toxic solvent that's commonly used in perovskites. This in itself, though, is really nice to know, but it doesn't necessarily relate directly to the economics of doing something. So we also developed a techno-economic model to define the the operating cost both of heating, cooling, and extraction of these vapors from a manufacturing center, combined with a reduced depreciation cost from the CapEx needed to actually do all of this stuff. So again, for a 1,000 meter cube sized manufacturing center, you do get a 22 times increase in manufacturing throughput. This is not based again on the theoretical limitations from the solution. Both THF and DMF would have very similar low flow limits, but they have obviously very different PEL limits as marked with the blue line. From a cost perspective, you also have about a 22 times decrease in manufacturing related costs. And I want to directly point out what I've marked here on the graph at 1 cent a watt. Today, silicon solar cells are usually sold between 10 and 15 cents a watt, with all CapEx, including manufacturing, roughly accounting for 4 cents of that. So a cent a watt is an incredibly high percentage in this scenario just for handling solvents. So if you take nothing else away from this, either the math or anything else, there's a good rule of thumb that you should be following in this field, which is that you shouldn't be using any solvents lower than about 100 parts per million permissible exposure limit. It's just going to be uneconomic and it can't actually scale. So how do we actually engineer systems to work within this regulatory framework? And so just to point out kind of the basics of ink synthesis, you know, at a very fundamental level, it's just dissolving a solid of interest into a solvent. This creates a solution. And we call it an ink because this is actually reversible. So you can take your solution, deposit it on a substrate, get the solid of interest in usually a thin film format. This works sometimes, not all the times. It's not often optimized, but in the perovskite academic communities, this is really what's done. The solids are perovskite precursor salts, and the solvents are usually majority DMF, but sometimes you can add additives like DMSO. From a more realistic level though, taking into account these OSHA-based regulations, you often have solids, but then you dissolve that in a multi-solvent system and you add other things into it to impart properties that you would be desirable. So adhesion promoters, wetting promoters for coating, coalescence to help film formation, and dispersants and ligands to help extend solubility regimes. And all of this is, again, designed specifically for engineering this process of drying into a quality film. And I'm not going to talk more about all the components of this, but the key takeaway is that just understanding the solubility limits of your solids is very key for designing better engineered inks. And high solubility limits allow for just better engineering overall. You have more tunable knobs. more things to change, and that ultimately leads to higher scalability. The way the industry has done this traditionally is through the Hansen model. It's a 3-component model, all with partial solubility parameters, so non-polar interactions, polar interactions, and hydrogen bonding. What's nice about the model is it assumes linearity. So if you take a multi-solvent system, all pure solvents will have fundamental DP and H's. You mix them together and you linearly combine the DP and H to get an equivalent DP and H for your new system. For solids of interest, there's one more parameter, which is the interaction radius. All this defines is the range at which it's soluble within Hansen space. So taking this in mind, we developed a novel ink system based on ligand chemistry and coordination chemistry with lead to fit within this space. This is really useful because there's about 1,000 components that have been identified and modeled that with Hansen. So this is directly applicable for engineering tons of systems. As shown here is all the ink systems that went into this model with the interaction radius of the methylammonium lead iodide. This is specifically methylammonium lead iodide formulation. Just to give your bearings on kind of where solvents sit within the space, THF is about here. More aggressive solvents like DMF and DMSO are in the higher polarity regime, acetonitrile as well, and then methanol, of course, is more hydrogen bonding that is polar within this model. But again, this is only half of the equation. So this only accounts for solubility. It doesn't account for going the reverse direction and making thin films. So within this space, we chose 2 ink systems for study, both THF and methanol, as well as THF and acetonitrile, to kind of get a sense on how this model performs when making thin films of interest. So one of the easiest things that you can do is obviously SEM based for morphology. And if you look at the crystalline domains, again, under SEM and pull out the boundaries as defined from SEM, there's 3 systems that we looked at here. Again, the binary mixture of THF and acetonitrile, THF and methanol, and then THF with a solution-based stabilizer. We then plot this out by the relative frequency of those domain sizes and fit it to a traditional log normal. This is very commonly done with grain size analysis. The actual size distribution doesn't matter here. What matters is that all 3 of these inks have the same distribution, which means that at least within these inks of interest, they're actually forming relatively the same film, which is really great from an engineering standpoint, because it means that this Hansen model is useful creating a wide variety of ink systems. This is further reinforced if we make devices from these inks. So in a traditional NIP structure of tin oxide, methylammonium lead iodide, and spiro, we can also, these are just showing the device statistics of forward and reverse scans. They're a little hysteretic, but again, I want to emphasize that the key takeaway here is that they're all the same, not that they're highly optimized at being highly efficient. That being said, however, the champion devices of the specific run were all about within 1% of each other, which is within the error bars of the power conversion efficiency, as well as the external quantum efficiency as well, with these features in the red likely being due to thin film based effects. So this is all well and good. But again, what we're really curious about is taking these small area ink systems and moving it to larger area slot die coating. So just to give a little bit of the basics, I'm going to show a few videos in a second. Slot die coating usually involves a stationary head. We inject ink somewhere into the die. It then flows through the slot down the die's length, injected out the bottom, and then dispensed onto a moving substrate. This is then dried a little bit uncontrollably into the crystallized film of interest. Like I said, drying can be a little bit uncontrolled. And so to improve uniformity, you can add an air knife. This, of course, is also along the same linearity of the moving substrate. But it promotes active drying and then gets you a much more uniform crystallized film. So shown here is the THF methanol ink. at about, it was about 0.9 meters a minute for frame of references on speed. And you can see that there's a very defined length, about a few centimeters, in which case the THF and methanol dry and create that crystallization front as you see there. With the active drying, you can expand your width of your stripe. The last one was half an inch, 13 millimeters to 25 millimeters. You can also run much faster. So this is 3 meters a minute, but you get much more uniform drying, much more unified films. And this is how we print perovskites here today. In collaboration with Tristan Watson's group and Rahul from Swansea University, we extended this to roll-to-roll based capabilities. So before was obviously our sheet-to-sheet coder. I do want to make a note that this is a change in device architecture, so PIN-based system, but the champion device here was about 13%, which shows that there is a very easy translation from the small scale devices, which again stabilized about 14, up to this champion device on roll-to-roll for 13. So at this point, I can't not talk about perovskite alloys anymore. And so again, they're a tertiary compound of the form ABX3, and everything I just discussed is only useful for methylammonium lead halides, also referred to as MAPI. This is unfortunate because it's actually the formidinium and cesium compounds that are generally considered industrially relevant. And so considering this and keeping the OSHA and EPA regulations in mind, we had developed a novel recrystallization method to access these alloys at scale. The process is very simple. We take our printed MAPI film as shown in the previous video. We treat it with a carboxylic acid salt of a cation of interest or a mixture of cations of interest. Ammonium carboxylates and specifically methylammonium carboxylates are generally either volatile, easily degraded with heat, or ionic liquids. And so under heating, these volatilize off the film. And through Le Chatelier's principle, cation exchange is chemically driven into the film. Schematically, this is shown here. We just take the MAPI film, treat it with formidinium acetate, heat it, and that creates our formidinium-rich film of interest. Here's a video of kind of this process happening. This is just a 1-inch film being placed on a hot plate. You can see immediately it darkens, showing the cation exchange, and then gases start coming off, leaving your recrystallized film. This doesn't need any washing, so relative to other two-step methods, this can be useful as is. And we also really think this is a useful process, so we're pursuing IP protection as well. From the transition from a methylammonium-based film to a formidinium-based film, you'd expect a shifting in the band gap, and that's exactly what we see. So between a methylammonium precursor as well as the exchanged formidinium, and again, this also works with cesium-based compounds, although I'm not going to be really talking about this much today. There's a very defined redshift in the absorption edge. This is also very true with the PL spectrum as well, which shows a peak height of around 805 nanometers with no off peaks. So you'd expect that potentially if it's not phase pure, you'd get something around 780 as well, which is the emission peak expected from a methylammonium iodide film. You can also look at X-ray diffraction, which is a chemical or a fingerprint of crystallographic materials. I want to make abundantly clear at first that the FA-MA-based films are very strictly perovskite with relatively little off phases, a little bit of hydrated phase up near 12. If we look at the characteristic peak around 14 degrees, we can again show that there is a shifting toward lower angles between the methylammonium lead iodide and formidinium FA-MA film. Plotted here also is a pure formidinium lead iodide film deposited from a DMF-based precursor. If we look at the theoretical peaks, the formidinium lead iodide corresponds pretty strongly with where the theoretical unit cell peak should be. But I do want to point out that THF-based routes, which were used here, both the MAPI and the FAMA recrystallized film have about a 1/4 degree shift to higher angles. So this means that we might actually be having a near full conversion of formidinium, but that peak alignment might be due somewhat to the solvent, although this is not necessarily really studied. Of course, this is great, again, on small scale, but we're really looking at translatability here. So for slot die coating, this process was also translated. The first step, again, this is a 2-step process. I've already shown it's a slot die coated ink with an air knife drying method to make a methyl ammonium lead iodide film. For the second step, we take this carboxylic acid based ink, coat it on top of the on top of the methyl ammonium lead iodide film, and then immediately dry it with an air knife, heated air knife. And this simulates kind of how this would work at scale with a forced air annealing oven. The end result is, again, the formidinium-rich FAMA film. I'm going to show a video in a sec again, so just to prime your eyes, the hot air knife is in the center here, the slot die steel on the edge. The wet film is coated here. It's a little bit dark. It's a 25mm stripe width. It dries, creating kind of an interstitial phase. And then from the hot air, which is 120 degrees Celsius, it forms this annealed recrystallized phase, which has a little bit of a gold color to it. So this is the recrystallization process. It's a little bit slower than the previous coating method, but this is nothing fundamental. It just is basically the size of our air knife and kind of the dwell time that we need within the annealing. But it is about, I think it's about ½ meter a minute or so to, again, prime the speed. From a kind of visual perspective, just to show you, all the films are black, pretty optically thick. So we have to look at PL uniformity to get any sort of knowledge about kind of what this process is doing. So from a methyl ammonium lead iodide film, it's relatively uniform over the 25mm stripe width, as well as 6-inch length. The recrystallized film, again, it's relatively uniform over the 25mm length. This lead-in defect here is common on small-scale sheet-to-sheet coaters. But I do want to point out that the speckling and line-based distribution is actually defects transferred from our vacuum bed. So the vertical lines are rough machining marks, and then the speckling is actually due to the hole patterns in the porous aluminum chuck. So none of these defects are actually fundamental to the ink system or the method. They're actually hitting up the limitations of our proofer. Similarly to small scale, we see similar peak shifting on a large area of films, both in the absorption onset, as well as in XRD peaks. These peaks also correlate with kind of, again, that 1/4 degree shift to higher angles, as we see in small scale, and they actually align as well to the small area peaks as well. Of course, what everyone's interested about is devices. And so in a traditional NIP-based structure of tin oxide, the recrystallized FAMA, and then Spiro, I want to emphasize this is not passivated. So there is actually higher to go here if we went with passivation routes. Our champion device today is scanned at 20.5% with a stabilized power output of about 19. EQE shows above 90% in generally the 450 to 750 nanometer regime. And both these things really reinforce that this is a method that not only can provide high efficiency devices, but can easily scale between small and large. With that, I am going to conclude the technical portion of my talk and leave the rest up for questions if you desire it. Today I've presented 2 things, the first being an engineering framework for developing scalable perovskite ink systems. And the rule of thumb takeaway from all of this is don't use anything lower than 100 parts per million permissible exposure limit. and ideally, from an EPA perspective, choose solvents that are not regulated as hazardous air pollutants. I've also presented a novel recrystallization technique for easily translating small and large area perovskite films. Again, I didn't talk about it too much today, but the power of this technique is that it's really alloy independent and that it can achieve very high quality films with power conversion efficiencies over 20%. With that, I'd like to get into, sometimes this is people's favorite portion of the talk, which is to thank everyone that made this work possible. I'd like to thank first my committee. Vladimir has been an amazing supervisor, incredibly patient. One of good friends of mine really mentioned that throughout your PhD, it's a rite of passage to have at least one sort of mental breakdown. And luckily, Vladimir is probably one of the most patient advisors I've ever known, incredibly helpful, and has been a true inspiration. Moonji, I don't know how you do it, but you continuously get great collaborators. Thoroughly enjoyed working with Nicole, as well as everyone else within your group. And Rajiv, thank you so much for all your insight on the techno-economics and thinking about how these films and devices can potentially be used. I'd also like to thank two more professors that have been instrumental throughout my time here. She was a student when I first joined, but Farnaz helped me greatly throughout my master's, none of which was talked about here. But I definitely wouldn't be as good at material synthesis if it weren't for her guidance. And I'd also like to thank Tristan at Swansea University. I would not know nearly as much about slot die coding or coding methods in general if it weren't for the fact that he allowed us to come visit for a full month, without payment, without anything, just come in and use the tools and get situated. I'd like to thank Vladimir's One Lab and the Grid Edge program for amazing support and collaboration. I'd like to specifically point out people whose work directly influenced the results today. So obviously Nicole Moody, who's on the call, thank you for coming. We collaborated for a long time on T-clip end-of-life testing and materials development. Doc and Jeremiah, who both contributed to developing the high efficiency devices. And then the undergrads I've had along the way who definitely, again, wouldn't be able to have nearly had as much data as I had if it weren't for them. Ming, who helped a lot with the THF optimization early on. Emma with the codings and techno-economic analysis. And Jay also with a lot of the coding and devices shown in my presentation. For external collaborators, again, thank you, Tristan and group. So Rahul did the roll-to-roll printing shown today, but Dan Burkett, who's also on the call, thank you guys for coming, supported us and has been very great collaborators for the last 4 years. David and James hosted Roberto and I when we spent time in Swansea. So thank you to you guys. Sarthak, I know a lot of your data wasn't presented, but thank you for doing XPS and top sims to help us get uniformity. Damien for providing a lot of industrial PV based materials that went into a lot of the analysis. A lot of you may know I've been working at part-time at a VC firm. It's been a pleasure working with all of you, and thank you so much for being an absolute great team. Nader, Aruna, Saba, Leslie, Farah, Paranaz, Samlin, thank you for putting up with me and my time-constricted nature. It's truly been a pleasure. Thanks to all the friends I've had along the way who keep me sane. So I've been a GRT for 3 years. So Putz for keeping it interesting. The GRTs at the time for bringing me back to reality. My lab, friends, camping, all those things. I'd like to thank my parents, sisters, family-in-law, for being rocks of support throughout the last 6 years, hosting me at Thanksgiving so I didn't have to travel and waste precious time. And then, of course, most importantly, my beautiful wife, who's been just a joy to be around all the time, permanent drinking buddy. She's in the other room laughing. Yeah, I'm excited to spend the rest of our lives together. And with that, I'll open it up to get back to the topic at hand for any questions that the audience might have. So how this will work, please raise your hand and just ask questions and I'll call on you.
We have a first hand raised. I believe Professor Marty Schmidt.
Hi, Marty.
Thanks, Vladimir. Thanks, Richard. Rich, you didn't talk too much about this, but I'm just kind of curious with the perovskite. How important is grain size, control of grain size, distribution of grain size in the sort of final performance? And did you have to optimize for that?
So SEM based grain size, it helps kind of. It's not very direct, so it's not the same as like if you were doing a steel, for example, and grain size has a huge impact on mechanical properties. With perovskites, they tend to be columnar, so the entire thin film tends to be 1 grain. So we usually don't have grain-grain transport. So from a device perspective that way, it usually doesn't affect it too much. But overall crystallinity and grain size does relate kind of arbitrarily to the lifetime of these materials, because grains tend to be where water ingresses first. Sarthak, who's on the call, did a really great study on grain boundary angle differences. The SEM features tend to be high angle grain boundaries, and so relatively high energy. And those are always the places that degrade first. So from a performance perspective, not all that much, but from a lifetime perspective, yeah. I can show you as well. I have a ton of backup slides. For the recrystallized films, just as kind of a comparison. So these are actually not even the best films I've had, but they compare pretty equally to a traditional formed annealing wet iodide film as done by DMF-based anti-solvent routes with grain sizes around a micron. Rahul did a nice study, so I stole his image for this. Thank you, Rahul, of doing methylammonium chloride additives, and we see a grain growth again in this recrystallization technique. It's a little hard to see, but the scale bar down here is also a micron. So these are in the field. This is relatively large grain sizes.
Okay. Thanks, Rich.
Which, if I can maybe just add to that, the question so the grain size itself does not seem to affect the performance of the devices tremendously. You haven't actually added, call it efficiencies here, but you're talking about maybe a few % back and forth between these. The one part that's unique about perovskites, and maybe you haven't emphasized it enough, is indeed their response to the defects, meaning the band structure does not significantly get affected by the defects. And maybe you can elaborate more on that.
Yeah, I'll put the slide up again. The defect tolerance comes from an iodine anti-bonding to lead anti-bonding transition. So a lot of dopants, additional based materials, things like vacancies and plane-based defects within the grain, they almost always go within either the valence or conduction bands rather than creating mid-gap states. It is still possible to create mid-gap states with various things, but because of that anti-bonding transition, they often don't. So, the precursors on these, again, they're simple salts, but we often don't use things like with super high purity. So, we buy materials like everyone else from TCI and a company called Great Cell Solar in Australia. TCI is chemically cured to 5,9, so that's the lead iodide precursor, and then the methylammonium iodide, formidium iodide, it's almost always 99%. It's very challenging to get higher than that from a chemical perspective. So we're not going nearly as pure as silicon-based system.
Great. Thanks.
Nicole, you're next.
Thank you, Rich. So great talk. I always love to see props used in a presentation. So really, really cool that you had those printed films literally on hand to show us on the call. So my question is, let's see that again. My question was, you mentioned there are both EPA hazardous air pollutant limits and OSHA permissible exposure limits. I was just curious, would those OSHA permissible exposure limits not fundamentally already be protective relative to the EPA air standards? Or is there some sort of threat of release due to improper storing of solvents or something like that?
Yeah, good question. So the OSHA one, yeah, there's a lot of nuance in this question. Thanks for asking it. So from an OSHA standpoint, there is permissible exposure limits that come into effect in atmospheric based internal things. A lot of the actual OSHA regulations from that table, and I'll pull that up, they're actually not breathing based, they're skin based. So even if you're wearing like a respirator or something to improve air quality, you're still going to be overexposing someone because it's actually going to be a skin-based limit. So there's that. That's just for exposure. OSHA also does storaging and what you can and cannot do with flammable stuff. That's not discussed here. EPA does internal like building based limits as well. Usually they're much lower, which is why most likely in a manufacturing setting, if someone was working around the solvents, they'd be wearing a respirator. From the emission standpoint, it's completely different. So it's not it's no longer an exposure amount. It's the amount of, first off, the amount of solvent that you're using, if it's a hazardous air pollutant, and then yeah, that's it. So they divvy it up actually by industry, which is why I didn't really talk about it. But for the coding and printing industry, if you're a major source, you have to reduce emissions of all hazardous air pollutants by 95%. So it's just broad. It doesn't relate to the tonnage amount. It's just broad. And how that's normally done is by putting it through catalytic burners. So it's just an extra CapEx cost. If you're a minor producer, you're subject to a little bit different things, but it's basically the same. You basically just can't really emit a hazardous air pollutant. So it's, yeah.
Please don't emit those. That'd be great. Thank you.
Ray has raised her hand.
Hey, Richard, nice talk. I had a question. I think I'm missing something, but when you were talking about going from the MAPI films to the FEMA films, so I guess the way I understood it, you were talking about an ion exchange transitioning from methyl ammonium to formamidinium. And so I guess in my mind, I thought, oh, you replace methyl ammonium with formamidinium, but then what happens to like the side products or like the methyl ammonium was my question.
Yeah, they're, I'm not gonna go back to the slide. They're extracted. They're actually volatilized off. So they become gaseous and then they're pulled into the extraction system. So we're just completely removing it from the film by it degrading, basically. Does that answer the question?
Yeah, and I guess, so does that also impact like the limits that you were talking about then?
It does. So methylamine is regulated to a 10 ppm limit, but it's only going to be the amount that you're actually depositing in thin film format. The molar amount of bulk solvent is going to be the vast majority of what goes into your airstream. So I did a equivalent. OSHA. I don't actually have a slide on this, sorry, but there is a way to calculate an equivalent permissible exposure limit, assuming all byproducts and not just a single solvent. So like mixtures of solvents. And with taking into account the volatilized methylamine, if that's the primary component that comes off, I don't actually know. But if it's methylamine, it's regulated to 10 ppm. And then the total equivalent of the solvent systems that I presented would be about 150 parts per million. So it's actually not as much to limit you. It drops it down a little bit, but not a ton. Acetic acid, which potentially is the other one. Yeah, that one's also not really that much. But I do want to mention that it's most likely not actually what's happening. It's probably coming off is degradation components. So like simpler like CO2s, things like that.
Okay. Yeah, thanks a lot.
Any other questions? All right. Well, what we're going to do is we need to step into the next part of the oral exam, this presentation, which is, Rich, I wonder if you can form a breakout room and send your committee and yourself into it. The rest of you, you're welcome to stay in the main room. We will keep Rich talking to us for a few minutes and then send him back.